Okay, so today we are going to continue the discussion on the shock waves. We are going to continue discussion on the Mach waves in general. And the first thing we are going to discuss is going to be the canonical shocks. But before going through that, I just have to mention that we are running a little behind our schedule, but that is all right because I think I said in one of the lectures that that's the schedule that I've posted on Blackboard is my wish schedule, my wish list, if you will, right? So I already knew going in that we are not going to make it. So don't worry about anything. We will cover whatever we have to cover for the course, and let's see how it goes. And yeah, so let's just start with the canonical shocks. Whenever you have a cone in a supersonic flow, what's going to happen to you is that you are going to get to canonical. You're going to have a canonical shock. Canonical shock is essentially a three-dimensional shock wave that passes through the cone, essentially. So it is some sort of a symmetric condition. So you can assume it is two-dimensional, symmetric two-dimensional, and do all of the analysis as a two-dimensional analysis. But you always have to keep in mind that it is a reality. It is a three-dimensional case, and it has to be treated as such. Okay, a cone in a supersonic condition actually treats the flow, usually meets the flow with a zero angle of attack because of its geometry. So whenever it's moving, we cannot have like a 2 or 3 degree angle of attack. It will always meet the flow head on. And our discussion here is limited just to the concept. So we are not going to go through any theories for that matter. But the main differences between the canonical shock and a regular oblique shock wave can be visualized here in these two pictures, essentially. If you have a plain oblique shock wave, essentially what's going to happen to you is that your flow is going to turn, right? And the streamlines are going to turn with the same angle, right? This is not the same thing that happens when you are dealing with a canonical shock, okay? First of all, the angle change is not going to be as drastic as a regular plane oblique shock wave. It's going to be a little more gradual, if you will. And the angle of this streamline is going to be different from the angle of this streamline. And that is as far as the streamlines and the visualization of the flow goes, this is the main difference. So instead of having just two angles, we are going to have three different angles here. We have the theta S, which is the canonical shock angle, right? That's the shock angle, right? The angle it makes with the horizon, right? We have theta C, which is the cone angle, and we also have theta, which changes from your cone angle to the shock angle, right? So this is just essentially in a canonical shock wave. This is not just a one value. It is not a constant value. It changes from the cone angle to the canonical shock angle. Is there any questions so far? Okay. So essentially, because of that, you can plot the theta C versus theta S, and you can get a specific condition. You can get the canonical shock wave for the cone angle, a maximum cone angle, right? So what it means is that your cone angle for each Mach number can be so big. For example, if you're dealing with Mach 5, your is around 55, right? And for that, your shock angle, if your pull angle is going to be higher than 5, your shock angle is going to actually go to infinity. Does that make sense? Which essentially means that you are going to have, what does that mean? Let me see. Let's brainstorm here.
So as you approach infinity, your shock angle is going to go as you're mounting.
But what does an infinity angle mean?
A normal shock.
Is a normal shock a shock wave with an infinity angle? It is 90 degrees, right? So it is not infinity. Essentially, what it means that we are going to get to an unphysical situation, right? That's why we stop the curves here, right? The curve doesn't go further. So it is not an asymptote, right? That makes sense. So what's going to happen as you go higher than this? Let's go one by one. Let's just start with type. Did you get the notes, by the way, from on Blackboard? Yeah.
I think go higher in the
Yes, the cone they do, right? So that's just to be clear. We are all on the same page. What I'm saying is that based on what you see here, because of the specific situation of this cone, this is actually the same thing applies to the oblique plane shock waves as well. But we didn't go over it in the. I think we didn't go over it in the shock wave. But this happens in a cone sooner, in a smaller degrees, in different angles because of the specific situation of a cone. So if your cone angle reaches like 60 degrees for Mach 5, your theta s is gonna go to infinity. And this is in mathematical terms, right? Theta doesn't go to infinity. That doesn't really make any sense for theta. That's for 0 to 360 degrees, right? So what does that mean? What's gonna happen? Because we can definitely construct a cone that has a higher cone width, right? Because that's pretty simple. And that can definitely be put in a supersonic condition, right? Because that, I mean, it should, yeah, that will happen. So what's going to happen to that cone if that's flow?
Well, I know in an oblique shock, I don't know, I assume it's somewhat similar. If you increase the angle of the wedge and it's greater than like deflection angle of the possible wave, it becomes detached.
Exactly. So yeah, exactly. It's going to be the exact same thing, right? The difference is going to be in an oblique shock wave, you are going to get, let's say, if you go back to the theta beta m curves, right? We had in you remember the theta beta m curves for an oblique shock wave, right? The idea was for thetas higher than this, you are not going to have an oblique shock wave. You're going to have a separated shock wave. So essentially, it means that your shock wave is going to look like this, and it's going to happen sooner. Okay. But when you are dealing with a cone, you are dealing with a three-dimensional case. So your shock wave is completely separated. It is going to look something like this, right? Does this make sense? So I'm pretty sure you have seen the shuttle reentries, right? The pictures of the shuttle, and you have seen this type of shock waves. That's the reason. That's because the shuttle has a very huge cone angle, right? And yeah, that's why you see this type of angle.
Say it happens sooner.
I mean, it happens earlier in the flow. That's why it is not a time dependence. So whenever you're dealing with shock waves, we are not dealing with time dependence. We are dealing with already established shock, so a steady state condition. And mainly because analyzing a shock generation is harder, right? Yes.
To you reach the max in the angle earlier at a Mach number. So we were talking about Mach 5, that happens around 6.
It happens earlier. So essentially, that's a very interesting observation. So essentially, what's going to happen to you is that when you're moving faster, right, you're forcing this shock to get closer to the cone. Does it make sense? Okay, so let's move on to the next topic, which is going to be the expansion waves. So we already know that the oblique shocks are compression waves in a supersonic flow that abruptly turn the flow and compress the gas in the process. So what does this mean? What's going to happen to the flow when you're dealing with an oblique shock wave, and oblique shock wave? What's going to happen to the flow properties, like pressure? Increase. What's going to happen to Mach number? Decrease, right? That's the idea of an oblique shock wave. That's the adjustment you need to make for your wing to be able, like, for the wing to see the flow. Okay, but as you have seen before, when that flow in the supersonic condition is going to leave your wing, we are going to need an adjustment again, right? Because the air surrounding your wing or the plane is moving at a supersonic speed, right? So the exit condition of the wing also has to be supersonic. So we need to have a mechanism that actually acts in the opposite way of a shock, right? That's what we call the expansion wave. So an expansion wave is a wave that causes a supersonic flow to turn again, right? The same as oblique shock wave. But it also causes the static pressure to drop. Is there any questions so far? So oblique shock wave acts in the opposite direction of an expansion wave. Expansion waves are isentropic. And this is a visualization of just one layer of an expansion wave, right? So the flow comes in, like an oblique shock wave, it turns, and then the velocity changes. There we have the velocity increases here in this case, right? And this is the turn angle. It's the effective theta, right? So the goal here is somehow relate these angles, these turn angles, and this mu is the Mach angle. This is the familiar, the Mach angle, right? So the difference, we're going to see this later. Is there any questions so far? Okay, so this is just a geometric relationship. We can actually relate this theta to velocity and this velocity to mu, right? We can write the balance there. We can find the relationship between the two. V plus dv over sine of pi over 2 minus mu is going to be equal to V over sine of pi over 2 minus mu minus d theta. So also keep in mind that this angle is pi over 2 minus mu, and this angle is pi over 2 minus mu minus d theta. So essentially what we are saying is that V plus dV multiplied by this is going to be equal to V multiplied by this projection, right? Okay, let's play with this a little bit. Let's move these to one side and the angles to another, to another side, we are going to get v plus dv over v, which is going to be 1 plus dv over v, right? And the other side, you are going to get sine of p over 2 minus mu is equal to cosine of mu. That's a trig relationship, right? And you can say the same thing for this. This will transform to cosine of mu plus d theta. It will become from your sine and cosine relationships. We can simplify the denominator here, or we can change the denominator to cosine of mu minus d theta sine of mu. Is there anyone who can explain this relationship to me? What happened here? Cosine of mu plus d theta is equal to cosine of mu minus d theta sine of. Don't worry about it. It's just a mathematical relationship, right? I'm pretty sure if you think about it, you will figure it out. So that's actually that we are dealing with very small angles here. We can simplify that further. We can simplify cosine of mu further. We can get 1 over 1 minus d theta times. We can actually move the cosine of mu to the other side, or divide this whole thing by cosine of mu. We are going to get to this 1 over 1 minus d theta tangent of mu, right? We also know that this relationship exists. 1 over 1 plus minus of it, epsilon, a small value, is roughly equal to 1 minus plus of that is epsilon. So if you have 1 over 1 plus epsilon, you are going to get 1 minus epsilon, right? So we can actually bring everything to the numerator here and just change this sign to the plus. So we are going to get this final relationship. 1 plus dv over v is equal to 1 plus d theta tangent of mu. Okay? So the changes of we can remove the ones, right? And we can simply say that the changes of v versus the original velocity coming in is going to be equal to changes in the angle of the streamline. The turning angle of the streamline will multiply by the tangent of the Mach angle. Is there any questions so far? No? Okay. So let's take a look at the before condition before it reaches the Mach angle. We can find the relationship between the Mach number and the Mach angle, which was mu. Tangent of this mu is going to be equal to 1 over the square root of m squared minus 1. Okay, just replace the tangent of mu in the equation we had from the previous slide. D theta is going to be square root of m squared minus 1 over dv over v. And we also know that v equals to m multiplied by a, which is the speed of sound. And the speed of sound is a constant multiplied by a square root of t, or gamma rt, right? Gamma r are constants. So a equals to a square root of gamma rt. We can change this to a constant multiplied by the square root of t, right? You can replace that there. So v is going to be equal to a constant multiplied by m, the square root of t. We can replace v, or before doing the replacement, let's do this. We can actually go back to the rule we saw in the previous, in 2 lectures ago actually. So this derivation rule, right? That when you have these sort of relationships, you will get you will also have this sort of relationship, right? dv over d is equal to dm over n plus 1/2 of dt over t. That was the natural log derivation rule, something like that, or logarithmic derivative rule. Does that make sense? Do you want me to like prove that for you to make it more clear, or it's pretty simple. Just take the derivative take the natural log from the two sides. Right? That's going to be ln of b, ln of n plus ln of t to the power 1/2, right? And then you try to take the derivative. That's it. Pretty simple. Okay, and we also have this relationship for temperature as it relates to the Mach number. It's going to be a constant multiplied by 1 plus gamma minus 2 over m squared. That's the inverse of m squared. So we can find dt over t. If you just replace all of these things that we have here and use that rule, we can find dt over t. We can find dt over t based on this, and then you plug that in the d theta formulation that you have. So the changes in the streamline angle after a Mach wave, essentially, is going to be related to the Mach number of a streamed wave. Does it make sense? D theta is going to be equal to the square root of m squared minus 1 over 1 plus gamma over 2m squared dm over m. Yes?
The m is the upstream.
Yes, upstream. This is a very, we are talking only about one Mach wave, right? We are not talking about a shock wave here. So the changes are very incremental. The changes in velocity and pressure are very incremental at this point. We are not talking about expansion waves yet. We are just talking about one Mach wave. Okay? And yeah, this shouldn't have been here. So you can take the integral from 0 to the maximum of that turn angle, essentially. And you can take the integral from 1 to m for the supersonic conditions, right? Supersonic Mach number is 1 to m to come up with this equation for the thing that is called a Prandtl-Meyer angle. And the Prandtl-Meyer angle is nu of m, right? So the turn angle after the Mach wave is essentially identified by an angle nu. This is a backing work, right? So you are familiar with nu. And it's going to be equal to the square root of gamma plus 1 over gamma minus 1, inverse tangent of square root of gamma minus 1 over gamma plus 1 multiplied by m squared minus 1 minus inverse tangent of square root of m squared minus 1. The Prandtl-Meyer angle again represents the turning angle needed to turn a sonic flow into a supersonic flow at a Mach n. Is there any questions? So you can see the changes of Mach angle as it relates to Mach number versus the changes of Prandtl-Meyer angle as it relates to Mach number. As we increase the Mach number, your Prandtl-Meyer angle reaches close to limit value. And as we increase the Mach number, your Mach angle is going to go to 0. So a combination of like millions of a lot of these Mach waves is called an expansion wave, and we specifically call this combination a Prandtl-Meyer expansion wave, which is going to be centered at a geometric expansion coordinate like this. So we have a lot of Mach angles that starts from here, right? So we can find a nu for the upstream condition. We can also find a nu for the downstream condition. And this angle, the wall angle here, is your expansion parameter angle, if you will, the downstream angle, is going to be equal to this nu of f. You're going to find with this equation, if you will, right? So essentially, let's say you're solving a problem, you have an expansion angle. Keep in mind that the angle we were working on was before this. So we were talking about the nu of this, the Mach number of this part, right? We don't really care about that part. We really care about the downstream part. So if you use the Mach number here, or the Mach number you want to have here, right? You have to deal with this, the nu of the downstream Mach number, downstream flow. Does it make sense? Okay. So you are either given this theta wall, or you are required to find this theta wall, that which is going to be equal to the Prandtl-Meyer angle. As your downstream Mach number approaches infinity, your Prandtl-Meyer angle reaches a limit of a square root of gamma plus 1 or gamma minus 1 over gamma minus 1 minus 1 multiplied by pi over 2. What does this tell you? This limit. What does this limit tell you? So the idea was, let me go back a little. The relationship we have here, just to be clear, the relationship we have here was for supersonic conditions, right? Let's say you are approaching an expansion wave at the sonic condition, m equals to 1, right? Your theta is going to be equal to the angle we calculate here. So you want to have a supersonic condition after the expansion wave, right? And you're approaching this at a sonic condition, okay? The theta of wall, that expansion angle, is going to be equal to your Prandtl-Meyer angle. But the general case of oblique shock waves, especially if you are dealing with oblique shock waves, is that you may actually approach this wall at an M1, which itself is supersonic, right? So you have to calculate a nu one for that using the equation, right? And then you have a nu 2 for the downstream condition, right? So your theta is going to be nu 2 minus nu 1. So what I'm saying right now, so my point is theta is always, the wall angle is always related to the Prandtl-Meyer angle you calculate. It doesn't really matter what your downstream condition is, right? It is always related to that Prandtl-Meyer angle. So it can be related to the subtraction of the two Prandtl-Meyer angles, or it can be only just the Prandtl-Meyer angle downstream the expansion wave, right? So, based on this explanation, what can you say about this limit value? So let's say, what is this limit value for air? Can you calculate it? It's just going to be a square root of 2.4 over 0.4, right? Minus 1 multiplied by pi over 2. So what's that value? That's the square root of 6, right? Right? What is the square root of 6? 2 point something? 2.5, let's say 2.5. Minus 1, 1.5 multiplied by pi over 2. What is that? That's 135 degrees, right? So the point is, if your wall angle is 135 degrees, now how can I show 135 degrees here? The wall angle is the angle it is making it here. So 135 degrees is actually this, right? If your wall angle is this, then your Mach number is probably approaching infinity or very, very high values. That's all I wanted to get to. So at some Mach angle, at some theta, your Mach angle is going to be so high, your Mach number is going to be so high that doesn't really matter if your wall angle is changing. We just assume that your new or quantum Mach angle, or we don't assume it, it's going to be constant and that it's not going to change that much because it's so high. The changes in Mach number is going to be meaningless. Does that make sense? I mean, it will have a lot of meanings, but as far as the expansion wave is concerned, it's going to be meaningless. The changes in Mach. Okay. So for this specific case, where you have to calculate the nu 2 and nu 1, for the downstream and upstream condition, your temperature ratio is going to be equals to what you have over there, 1 plus gamma minus 1 over 2, and 1 squared over 1 plus gamma minus 1 over 2, and 2 squared. And we can also have the pressure ratios, P2 over P1, multiplied by 1 plus gamma minus 1 over multiplied by n1 squared over 1 plus gamma minus 1 over 2 and 2 squared to the power gamma over gamma minus 1. Okay. And we will definitely solve some example problems, hopefully on Wednesday. On Wednesday, we will solve some example problems from the shock wave, expansion wave, and the flow conditions that I will explain later. Is there any questions so far?
Just to clarify, is the wall angle measured from the upstream streamline?
Here. This is how you measure the wall.
Right, but that line that's being measured, what is it now?
You just continue the. Well, essentially, it's going to be the downstream streamline, yeah, the horizon. So. Okay. So, if there's no question, then we are going to move to the Rayleigh flow. Rayleigh flow. So we, at the beginning of this chapter, we talked about frictionless constant area or variable area actually flow without heat transfer. So adiabatic, frictionless, variable area. But right now we are going to talk about frictionless constant area and with heat transfer. So the only thing that is changing is that the only two things that are changing is that we are dealing with a constant area and it is not adiabatic. But we are dealing with the flow, we are still dealing with the flow in a duct. Okay? So you have your inlet conditions and dot and T1, T1, and you have your outlet condition and 2, T2, T2, and you have constant efflux coming in at the duct walls. Okay? Continuity equation or conservation of mass actually equation is going to be rho 1 u1 at the inlet has to be equal to rho 2 u2 at the outlet. Okay? The momentum equation is going to be rho 2 u2 squared minus rho 1 u1 squared is equal to p1 minus p2. We can actually move the inlet condition to one side and the outlet condition to the other side. So we can write it as p1 plus rho 1 u1 squared equals to p2 plus rho 2 u2 squared, which means that the fluid impulse is conserved. Okay? Did we talk about fluid impulse? I think so. Right? Like it was on density, yeah. So P plus rho u squared is called the fluid impulse. So the total heat rates going in to your system is actually going to be equal to m dot, the total enthalpy of the inlet minus total enthalpy of the outlet. Okay, which means that we can divide Q by m dot to get the heat rate, which is a very simple conservation equation. Your enthalpy, total enthalpy at the outlet is going to be your Q plus enthalpy at the inlet, which essentially is telling you that the only way your total enthalpy is increasing is by adding this heat, by adding the heat. Is there any questions? Pretty simple, right? And we can find the pressure ratio for this type of flow using this equation, 1 plus gamma m1 squared over 1 plus gamma m2 squared. We can find the density ratio using the conservation of mass equation, rho 2 over u1. u1 over just a rearrangement of conservation of mass, right? u1 is m1 a1, m2 m2, and essentially these relationships we already have had, right? The same is true for the other one, P2. We are just going to use the ideal gas law to replace rho with P2 P1 and P1 multiplied by P2. Okay? Which means that we can have two main equations for the temperature ratios and pressure ratio and density ratio, right? m2 squared over m1 squared, and the rest of it. Same is true for the density. Is there any questions here? These are very long equations, so I'm just going to give you a couple of seconds to write them down if you want to. But the lecture notes are posted, and Tyler actually had asked me over the weekend to post the lecture notes before the class, and that's what I'm going to try to do, right? Yeah. So we can actually, we have to, not we can, we have to, because we have the heat transfer, we have to relate the total temperature change or total temperature ratio as the inlet and the outlet to the heat input, right? So we already know the relationship between the total temperature and the regular temperature. We can find the ratio. We can transform that ratio based on the ratio we had from the previous slide to something that is only a function of Mach number, and then you can just simply say it is equal to 1 plus Q over Cp multiplied by total temperature multiplied. Right? Okay. This is not what I want to. Okay. So we will go over those equations later because we have to explain this and then go over them. So we can actually have a TS diagram for this case, for the case of cooling. Let's say you start at your inlet, you start somewhere here, right? And we are dealing, let's start with the subsonic condition. So we are dealing with a subsonic Mach number, right? At a specific temperature. You are heating your flow, right? Which means that your temperature is going to rise, right? And you are heating your flow. And at some point, the changes in temperature with respect to entropy is going to be zero, right? And that's actually, for that specific case, your Mach number at that specific point is going to be equal to 1 over square root of gas, right? So for each gas, that point reaches a different position. But what's going to happen afterward? What's happening afterward is that in that same duct flow, what you're going to see is a decrease in temperature, right? You're heating the flow, you're not cooling it down, but you're going to see a decrease in temperature. And we can actually explain that using this equation. So this is something that you can see in this equation. But what I wanted to get to before talking about that equation is that at some point your Mach number is actually increasing, right? At some point it will reach the sonic condition. So what we are talking about here is the flow in a duct what we are talking about here is flow in a duct, and we are talking about different positions of that flow, different locations in that flow. You may never reach those positions based on the length of your duct. Yeah, so that's a very important factor. Let me actually explain it on the PowerPoint here. Okay. So the idea is in that TS diagram, let's say you're starting with a subsonic Mach number. You are heating this up, your temperature is increasing, right? And at some point, the changes of temperature with respect to entropy become zero, and afterwards, your entropy increases, right? Your entropy is increasing, but the respective temperature for that specific entropy is going to be lower than your respective. So you are having a higher entropy but lower temperature. Okay? Doesn't really mean that your flow is cooling down, but for a lower temperature you are getting a higher entropy. Does that make sense? It shouldn't happen, right? It is happening, so it should happen, but which doesn't really make that much of a sense to us, right? But the point is, at some point, your Mach number is increasing as well, and you will reach the sonic conditions, which means that at some location in this flow, we will have the star condition, the sonic condition, right? So we should be able to relate the equations we have. We have to use the sonic ratios as well. And these are the ratios we have seen before, all of them, right? So P over P star, Q over T star. If your sonic condition reaches at the outlet, meaning that your M is 1 at the outlet, then this is essentially your T2, P2 over P1 over P2, right? And so on and so forth. Okay. You can use the Gibbs law to find the changes in entropy. Just play with the equation a little bit. These are the derivations part. I'm not going to go over. This is the final equation you are going to get for the changes of entropy in a Rayleigh flow. Okay? The changes of entropy can be represented by Cp multiplied by dT over T plus R multiplied by 2 gamma m squared over 1 plus gamma m squared dm over n. Okay. So if we, let's go here again. So what do you think is going to happen when you are at the sonic condition? So as I mentioned, as you are moving in the dock, right, your M is changing, right? Your M is actually going from subsonic in this case, and this is called the Rayleigh line, right? So you will get an M1, right? But does it go this way? What I mean is that, let's say we are in that same dock, and here you will get to M equals to 1. What is the velocity afterwards? What is the Mach number afterwards? Is it M, and we have started with M smaller than 1. Is it M larger than 1? Is it supersonic condition? Yes or no? Slight drop? You mean like, so it's gonna go back on the curve? Is that what you mean? So just guess, right? Just guess and try to explain your guess. Let's start with Ryan.
There'd be a shock wave over the top number.
Okay. Shock wave in a subsonic flow. We started with subsonic flow, right?
To get to Mach 1.
You get to Mach 1, we don't have the supersonic yet. Right. So can the Mach go further than 1?
Are we saying it's just traveling Mach 1?
At some point it reaches at Mach 2, Mach 1, right? And it starts at the subsonic flow, the velocity is increasing because you're heating it up, right? At some point it will reach Mach 1. What's going to happen afterwards?
Temperature come into play too, possibly down change.
But we are heating the flow up. How is it cooling? I think I mentioned the temperature will cool on. I shouldn't have said this. What I meant is you will get higher entropy for lower temperature, right? That's what I meant. So for cooler temperature, you will get higher entropy. It doesn't mean that this is going to happen within your flow, right?
Yeah, so it'll be greater than 1.
Pardon me?
There's higher entropy, then we'll go further.
It won't go?
It will.
It will go over than 1. But then, based on this plot, if it goes over than 1, your entropy is going to decrease. But that cannot happen, right? When you're in a process, your entropy is either remains constant or always increases, right? If that doesn't happen, if you are in a process and your entropy decreases, then you are violating the second law. Essentially, you can build a train that can move and cool the surrounding, right? That cannot happen.
So why on that curve is entropy going down at?
This doesn't talk about the process, the same process. This just shows you that you can get this amount of entropy for 2 temperatures. Okay, that's actually my question. Can we go further? If you start from subsonic Can we go further than this?
Oh,
This is the maximum we can go. So the Mach 1, if you start from subsonic, this is the maximum we can get, right? And then you can have another plot. You start from supersonic, right? And get to Mach 1.
So is that like similar to sonic flow?
Exactly. That's what I want to get to. So we actually, using a constant area dot, we can build a nozzle or a diffuser. We can have choking conditions. We can have throttling conditions, right? So at some point in the flow, if at the middle of this you get to M1, you have a choking, you have the choking condition, or you have the throttling condition, right? But then the question is, what is going to happen if we get to these conditions? Okay, let me see if yeah. So we can find the entropy using this equation as well. But yeah, let's say we have reached the sonic condition. Let's go back to that plot. Let's say we have moved with n smaller than 1, okay, and we have reached the sonic condition. What's going to happen? But we are at the choking, right? And it is not like the variable area that we just added we just changed the area variation, right? It's just a constant dot, constant is being applied.
you'll get some backflow.
You'll get some backflow, exactly. You'll get some backflow on the dot. So that's it. The adjustment of the flow is that at the inlet you will get some backflow, right? So if the flow actually adjusts itself, so you will get the sonic condition at the outlets. Okay? Does that make sense? So what's going to happen when you are reaching this sonic point with supersonic conditions, with Machs higher than 1? For subsonic flows, you will get backflow. What is the adjustment mechanism you have for supersonic conditions? Shock waves, exactly. So at somewhere within the flow, you are going to get the shock wave. We actually, I'll talk about it later. Okay. And the mu inlet temperature, if you will, we always use the Prime condition to show the inlet temperature or the mu inlet properties when you have the backflow or when you have the shock wave generation at the inlet, right? Because the velocities at the inlet will change, right? We just show them with the 1' and 1'. And we are not going to calculate those for this type of flow. We may do it for the other type of flow, the Fano flow, which we will talk in a second. But yeah. So essentially, when you are dealing with a lower Mach number, what's going to happen is that the flow is going to spill over the dot, right? It cannot go in because of the choking condition. It's a variation of the ratios of everything you have, the temperature, pressure, and everything with the Mach number. And that's it for the Rayleigh flow. But for the Fano flow, there is another type of flow, which is adiabatic, constant area. We are going to deal with a calorically perfect gas, perfect fluid or gas. But the difference is going to be we do not neglect the friction, right? So conceptually, it is basically the same thing as the other two, variable area or heat transfer, right? It's the same ideas. We have some choking conditions. We have the TS diagrams are going to be look like that, right? But we want to find, I forgot to put the animations here. But we want to find the equations that govern this type of flow, right? To do so, instead of dealing with the inlet and outlet, we are going to talk about one small element of the duct. Who can tell me what's the reasoning behind this? Why are we dealing with only one small element of the duct versus the other type of flow where we only dealt with the whole duct? We didn't just try to find a small element. Exactly. So the thing is, the friction changes as you move in the duct, right? Because friction is a function of fluid properties and flow properties as well, right? As well as the wall condition, right? Remember the boundary layers and everything. So yeah, the friction is, the wall friction changes. What is the main equation we have for the wall friction? Negative mu du over dy, right? So the friction, the stress, the wall stress, wall shear stress that represents the friction is related to velocity, right? But if your velocity changes within the duct, then you cannot just have a big picture view of the duct. You have to look at small elements, right? So let's write the continuity, the conservation of mass, momentum, and energy equations for these small elements. We have flow coming into the element with P, T, rho, U, and we have the flow going out with P, T plus dP, with all of the dP, dT, and d, rho, and du variations, right? And the length of this small element is d of x. So conservation of mass equation is going to be rho u multiplied by, it is going to be equal to the exit condition, that is rho plus d rho, u plus du, right? And if you just play with this, you can get to the following equation. Rho du is going to be equal to negative u d rho. Okay? It's clear? And you always have to keep in mind that when we are multiplying two derivatives, we always neglect those because it's going to be very, very small. We can play with that equation to get to this form of conservation of mass. D rho over rho is going to be equal to du over u, right? And the momentum equation is actually going to look like the same as for the conservation of mass equation. It's going to look the same as the variable area momentum equation with a big difference. I forgot to put on the animations here, but I wanted to ask you guys to write this momentum equation for me, right? So if you write the momentum equation, because of presence of friction, you have to add a friction term to your momentum equation because friction is going to be an acting force on your body. The pressure force is not the only force. The shear force is also there. But how can we calculate the shear force? We have to have the shear stress and then multiply by the circumference of the duct multiplied by dx divided by the area. Okay. To make everything simpler, we define the hydraulic diameter of a duct because some ducts are circular, some ducts are rectangular. So we have to be able to find a parameter that works for all of them, not just the radius for them. Who can tell me what was the definition of hydraulic diameter? Or what was the equation we used to calculate the hydraulic diameter?
gonna talk to you with them.
So let's start from here. What is the hydraulic diameter of a circle? It is its diameter, right? You have had heat transfer, right? You haven't had heat transfer yet. Okay, so you are excused. That's all right. But you three.
I'm guessing it's 2.5.
The hydraulic diameter is
On the circle.
in a circle is the diameter, just the regular diameter, right? Well, how do you calculate the area of a circle? Area. Pi r squared, but if you want to represent it with diameter, it's going to be pi d squared over 4, right? What about the perimeter or the circumference? Pi multiplied by d, right? How can we get the combination of these two to the diameter? Pi d squared over 4 and pi d. And whenever I forget the hydraulic diameter equation, I go from here. So hydraulic diameter of a circle is d, right? And it is the hydraulic diameter is related to area and the circumference, right? Area is pi d squared over 4 for a circle, and the circumference is pi d, right? How can this be equal to this, right? These will cancel out, right? We only have one extra 4, so you just multiply it by 4. So the definition of hydraulic diameter is 4 multiplied by area over the perimeter or the circumference, right? Does that make sense? That's the, and there is a definition. Right? This is not an equation per se. Okay, so if you were dealing with a rectangular duct, the hydraulic diameter would be 4 multiplied by, let's say, a square duct. 4 multiplied by length times width, right? Over, if it's a square, yeah, 4, right? That's right. Okay. So we are going to replace that here. We're going to use the hydraulic diameter here. So your equation, and then we're going to try to simplify the momentum equation. Your equation is going to be rho u du is equals to negative dp minus 4 shear stress of the wall dx, which is this length over the hydraulic diameter. Okay? So for the previous cases, what we had was rho u du is equals to negative dp, right? And then when you write it for the inlet and outlet, you're going to have rho u1 plus p1 squared p1, right? So for that case, we could have said the fluid impulse is conserved, right? Because it was conserved, right? We said p1 plus rho 1 u1 squared is equal to p2 1. But can we say that here? No, because of this friction term, right? So if you take the integral, essentially what you're going to have is going to be p1 plus rho 1 u1 squared is equals to p2 plus rho 2 u2 squared plus the integral of whatever this term is, right? So the fluid impulse is not conserved when you're dealing with the Fano flow. Okay? So if you write the energy equation, you are going to get this dH plus u du is going to be equals to 0. We can also write that in terms of total enthalpy or Cp dt plus u du. And we can rearrange, we can replace a lot of parameters, and we can actually have many different forms of energy equation which we have used throughout this chapter. Yeah. Is there any questions so far? So again, the goal here is to find the pressure ratios as well as the total friction force that you have there, right? Okay. Let me ask you this. What do we use, and if you have past aerodynamics or fluid mechanics, you should be able to answer this question. What do we use to represent the friction of a wall? What is the one parameter that is used most widely? Friction coefficient. I can give you the answer, right? Friction coefficient. Because we are running out of time, so I have to go a little quicker, right? So friction coefficient, so we wanna be able to write the momentum equation in terms of friction coefficient, and the definition of friction coefficient is this: the shear stress of the wall over rho u squared over 2, right? To find this, we essentially divide the momentum equation we already had by rho u squared, and this is what you are going to get. So that's a momentum equation that has friction coefficient in it. And the friction coefficient in general is a function of Reynolds number, the duct diameter, and surface roughness of the wall. But with higher Mach numbers, supersonic conditions, the local Mach numbers also becomes very important in this analysis. And in the friction coefficients, the value of the friction coefficient, we can find the total friction coefficient of the duct by just taking an integral on the local friction coefficient from 0 to L, right? And since it is going to be a function of Mach number, then we are dealing with the higher Mach number flows, which is the thing that's going to happen in this course, right? You have to be able to find the relationship between the friction coefficient and the local Mach number. To be able to do that, we are going to use one of the forms of the energy equation we had in the previous slide. We are going to play with that a little bit and replace some parameters. So you can actually, based on this, we can relate the friction coefficient to the temperature and the variations of temperature, as well as the Mach number and the changes in density. So you essentially have everything in one place. You can still play with this a little bit to get to this equation. And then one final equation, which is going to be this equation, is going to give you the variations of temperature. Is going to give you the local friction coefficient as a function of variations of temperature and the Mach number and the hydraulic diameter and the small elements of x, right? So let's say I want you to find the total friction coefficient, right? What should we do here? Take the integral. Simple. Yeah. Just take the integral here. This term will give you the CF, the large CF. Then the hydraulic diameter is constant because it's a constant area duct, right? 2 is constant. The problem is going to be taking the integral here, right? dt over dt. If it was only dt over t, then it would have been a simple integral, right? What would be the solution to that? Natural log, right? But the thing is, the idea is your n is also changing, right? So it is not a very simple integral, but it is doable. So in order to find a solution to that integral, we are going to find a relationship between temperature and the Mach number, right? And we have the temperature ratio, the total temperature to regular temperature, the static temperature ratio. We have seen this relationship many times by now, right? The total temperature is going to be equal to T plus 1 plus gamma minus 1 m squared, right? So if you take the derivative, if you actually use the the logarithmic derivative law, rule, whatever we had, we can actually come up with this type of equations. Is there any questions here? It's just the logarithmic rule, you transform that to this. Okay. So for this case, you have the dm, you have the dt, and you have the changes in total temperature. The idea is we are dealing with a friction with a constant area. In the case of a constant area, we know we transfer, so the changes in total temperature are 0, right? So this whole thing is going to be dt plus whatever we have here, plus the is equal to 0, right? So this means that we can replace dt by dt by something multiplied by dm over n. Okay? In the equation we have in the previous. So let's do that. Let's replace the term we had, and this is actually the simplified version. So this is the equation you are going to get. But we can also, in order to simplify the matter a little more, I don't know how simple is the second one, but it is a little simpler. We can actually change dm to dm squared, right? What is dm squared? It's 2m dm, right? So if you divide this whole thing, or multiply and divide this whole thing by 2m, and you'll get 2m dm here, you can get dm squared, right? And then all of the m's will be m squared. So 1 minus m squared, gamma m squared, here, and then m squared here in the denominator. Is this clear? So we have an equation that relates the local friction coefficient only to the Mach number. We don't have the temperature, we don't have pressure, we don't have anything else. Only to the Mach number at that location. And you can actually take the integral for this case. What time is it? I guess we have to. Let's stop here. Is there any questions? Let me just stop the recording.